So I hope this is very much clear to you, right? So now I am moving to construct the energy diagram or a correlation diagram or the molecular orbital diagram. I'll start with the very simplest molecule of the hydrogen, and then I'll extend this particular theory to the other diatomic molecules as well. So this is my next slide. What I am showing here, I'll show you here, the molecular orbital diagram of hydrogen atom, and molecular orbital diagram are also known as the correlation diagram, since we are correlating the energies of the energies of the orbitals which have identical energy. Please remember, right now whatever I am discussing the correlation between those molecular orbitals or those atomic orbitals which have identical energy. I am assuming no mixing here, right? No mixing I am assuming here. Later on, after the completion of this particular lecture, I will also explain the mixing of the orbitals which have the comparable energy, right? So let us start with the hydrogen molecule. How we can draw the molecular orbital diagram for hydrogen molecule. So this is your hydrogen atom, atomic number 1, configuration is 1s1, right? Similarly, you will have another hydrogen atom of this kind, because it is a diatomic molecule, it is another 1s1. So now how we can construct the molecular orbital diagram, right? So it is very important to understand these things. So first of all, draw a big line on this particular axis, right? And then make arrow on it, right? This is basically energy which is going up. So I'm writing energy here, okay? Energy. These energies are the energy of the atomic orbitals as well as the molecular orbital, right? And then what you can do, you can divide your page into the 3 different columns, just like that, right? One this one and another one is this one, okay? And then what you can do, on the left hand side here, you will write atomic orbitals of hydrogen atom. Here on the right hand side as well, you will write the same thing, because it is a diatomic molecule. Atomic orbitals of hydrogen atom, and in the center you will write molecular orbitals of H2 molecule. Please remember, beginners, please be careful while writing these things. Here we will draw the atomic orbitals, here again we will draw the atomic orbitals, and in the center we will combine these atomic orbitals to get the molecular orbitals. So what is the electronic configuration of hydrogen atom? I can write like that, okay? Say this is your 1s of the hydrogen atom containing only 1 electron in it, okay? And just parallel to this, please remember, just parallel to this, you will draw another 1s orbital of the hydrogen atom. Again, it will have the 1 electron, right? Please remember, see, whenever you are drawing this one, these must be in the same horizontal line, because they have the identical energy, right? And it is always good to write not to the scale on such plots, not to the scale. Since we are not taking any graph, we haven't decided any, or we haven't shown any scale, energy scale here. So it is always better to write the not to the scale here, okay? So now I'll apply the first assumption of your molecular orbital theory, which is what? Atomic orbitals combine to give molecular orbitals, right? So these 2 atomic orbitals are combining like that, and they will form the 2 molecular orbital like that only. These are the energy orbital, right? So this was the first assumption, if you remember, right? What was the first assumption? Molecular orbitals will combine to give the atomic orbitals will combine to give you the molecular orbitals, right? and number of atomic orbitals combining will decide the number of molecular orbitals formed. Since we are combining two atomic orbitals here, that means two molecular orbital will result here, right? And out of these two molecular orbital which will result in this process, one will have lower energy than the combining atomic orbitals and other one will have higher energy than the combining two orbitals. So this one is having lower, this one is having lower energy compared to these two. Since it is having the lower energy, so it's a bonding molecular orbital, and this one is having higher energy compared to this one. Remember, energy is going up, right? So this is having higher energy than these two, so this is anti-bonding molecular orbital, right? Since we are combining both these s orbital, and you know, whenever your s orbital combined, they always form sigma bond. Since it is the lower energy orbital, so it is the bonding molecular orbital. Similarly, one bonding orbital is forming, then definitely one anti-bonding molecular orbital will also form in that case. So this was the assumption. See, two atomic orbitals are combining, two atomic orbitals they are producing, and half of them, that is one, will have the lower energy than these two, which is the bonding one. Other one is having higher energy than these two, which is the anti-bonding one, right? And since this s orbital is centrosymmetric, I have explained you a little earlier that sigma bonding is basically your G rate. It is centrosymmetric, and sigma anti-bonding for s orbital is un-G rate, right? That is uneven, odd. So it is not centrosymmetric. So you can write sigma anti-bonding U here, right? So only these two molecular orbitals can form in that will form in that case, right? Because only two atomic orbitals are combining. Now you can count the total of electrons present in the two atoms. One electron is here, another electron is here, because atomic number is 1 for the hydrogen atom, that's why 1s1. But in total we are having the two electrons. Now we will fill these two electrons in the molecular orbitals, and I already told you molecular orbitals can also accommodate maximum of the two electrons. So that means this can accommodate two electrons, this will also accommodate two electron. And you know, according to the Aufbau principle, the molecular orbital or the energy orbital, atomic orbital which is having the lower energy will be filled first. So this is having the lower energy, so this will be filled first, right? So what will happen? Both the two electrons will go to this particular molecular orbital with the opposite spin, because we have to follow Pauli's exclusion principle as well, right? So this is the molecular orbital diagram of the hydrogen atom. Now if you want to know the bond order in that case, right? So if you want to know, if you want to calculate the bond order, so you will write the BO, bond order equals to what? Number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbitals. They should be divided by 2. So you know, this is the bonding molecular orbital which is having the 2 electrons in it. So what you will do, you will write 2 here, and there is nothing in the sigma anti-bonding molecular orbital, right? So what you will do, you will write minus 0. This should be divided by 2. That will give you the value of 1. So bond order for hydrogen molecule is 1. That means hydrogen is connected with the another hydrogen atom by only one single bond. Please remember, by only one single bond. And you know, the bond length, this bond length, please remember, sometimes it is also not so very important, but it is always good if you remember some of the data. However, it is not very important to mug out all the data, especially these bond length values and all these things, right? But if you can remember, then it is good, right? So the bond length for this is basically 74.2 picometer. And you can always convert this picometer into the nanometer, right? Or into the, not in the nanometer, because nanometer is very, very nanometer is generally not used to in the determination of the bond length. You can convert it into the angstrom, right? And if you like, then centimeter as well, meter, millimeter as well, right? By the convergence, okay? And then you see here, now suppose this is the correlation diagram. I hope this is quite clear to you. Now suppose someone asks you, what about this molecule? Say someone asks you, draw the molecular orbital diagram of dihydrogen positively charged ion, H2 positive ion, right? Now you know this positive charge is over there on this particular molecule. That means it is one electron deficient. It is one electron deficient. Okay. So this molecule now will have only one electron, right? Because it is having one positive over there. That means how you can draw the molecular orbital diagram, right? So for this, what you will do here, you will remove one of the electron and one of the atomic orbital, like that only, right? And then since now I am having only one electron, right, here only, so this will also have only one electron. So I can remove one electron from here as well, right? So this is how the molecular orbital diagram of H2 plus looks like. Okay. Now if you want to calculate the bond order for this H2 positive, bond order for H2 positive, BO. So number of electrons in the bonding molecular orbital, only one. Anti-bonding in the 0 over 2. That means 1 by 2, 0.5. 1 by 2 or 0.5 is the bond order. Half bond order is there. And since this bond order is very, very low in that case, right? Half. That means this molecule, this particular ion is not a very stable one, and this bond length will also be very, very high in that case, in case H2 positive. So what would be the bond length? If you want, then I can write like that. H positive you can write, and please remember this value is quite large. It is 106 picometer, right? And when bond length increases, that means bond strength decreases. So it is a weak bond. It is a weak bond. And this one is the strong bond. So this molecule is this hydrogen molecule is quite stronger than your H2 positive molecule, right? So whether it is your H2 positive, right, and or your H2, anything you are having, then you can draw the molecular orbital diagram for this one. Okay. Now suppose if I want to draw the molecular orbital diagram for helium, so this is your He2, whether it is see, now we will decide whether He2 will exist or not. So here you will write atomic orbitals of He, here again atomic orbital of He, and here you will write atomic orbital of He2. So I can write little bit more in a more clearer way, He2. Okay. And of course this positive I don't need here, right? So you know when you have your helium, right? Helium is having atomic number of 2. The configuration is 1s2. Okay. That means s orbital of the helium will have the 2 electrons. So 2 electrons here. Similarly, 2 electrons here, right? So molecular orbital diagram will remain the same. Now you are having total of the 4 electrons, 2 and 2, 4. And you know each of the orbital can accommodate only 2 electrons. So you can write second electron here and then 2 electrons here, right? So 2 electrons in the bonding, 2 electrons in the anti-bonding. So if you want to calculate the bond order for He2 molecule, so in the bonding molecular orbital, you are having 2 electrons. In the anti-bonding, you are having 2 electrons divided by 2. 0 divided by 2 exactly equals to 0. That means there is no bond. 0 means there is no bond between the 2 helium atom. That's why He2 diatomic does not exist. He2 does not exist. He2 does not exist, right? He2 does not exist because we don't have any bond order between them, right? This is, I hope this is quite clear to you. Okay. Now suppose you are having say He2 positive, So what is the meaning of that He2 positive, right? That means it is one electron. In the earlier case, you have seen this thing for hydrogen atom. Now it is for helium hydrogen molecule you have seen. Now this is for your helium molecule. Positive charge is over there. That means it is one electron deficient. Helium is having atomic number of 2. 2 such helium atoms are giving these configuration of the atoms, right? But now it is positively charged. So either of these two will lose one of the electrons. So I am removing one electron from here. Okay. And again, see, now I am having only 3 electrons. So 2 electrons in this. This can accommodate maximum of 2, but only available electron is 1 because 2 and 1, 3 only. So I'll remove one electron from here again. Now again, if you want to calculate the bond order for this one, so in the bonding molecular orbital 2 and in the anti-bonding molecular orbital, this is 1. So it is 1 by 2. So this helium He2 positive, this He2 positive is more like your H positive, right? It is more like your H positive. That means in a certain state, like say in gaseous phase or somewhere, this He2 positive can exist. He2 positive can exist, right? I hope this is quite clear to you. So this is the molecular orbital diagram of He2 positive and your H2 and H2 positive. Both I have explained to you, right? Now moving a little bit further, right? Guys, you can see this particular slide is very, very important. Please remember, I have taken this again. This I have taken from the Advanced Inorganic Chemistry, Shriver and Atkins. Here you see, this is the molecular orbital diagram of the atoms from lithium to nitrogen. See, hydrogen and helium I have explained to you. If you want to construct the molecular orbital diagram for the lithium up to nitrogen, like lithium, right, then beryllium, boron, carbon, nitrogen, all will follow, all will have this same molecular orbital diagram, right? So what I can do right here, from lithium to carbon, they all will have the same your molecular orbital diagram, right? But it will change for the oxygen and the fluorine, right? It will change from the oxygen and the fluorine. Why? You see here, up to nitrogen atom, there is no problem here. In that case, you see pi bonding is having lower energy. This is pi bonding, ungenerated one. It is having lower energy, and your sigma is having higher energy, right? This is up to nitrogen and this remains same, right? But when you move from nitrogen to oxygen, then you see this sigma bond basically, right? This sigma bond is having lower energy, which is this one, right? And then pi is having the higher energy. This energy order alters in that case, right? This is the reference, right? Shrivers and Atkins. Why this happens actually? This is again very important to understand why it is actually happening. See, when you move across the period from lithium to nitrogen, right? See, if you are moving from here to here, I can write like that. Here, you are moving like that. So your atomic radii decreases, or I can write atomic size decreases. Your atomic size decreases, right? That means your oxygen have little bit lower atomic radii than the nitrogen. What happens actually, when the size decreases, then these energy of the orbitals, especially your px, py, pz, their energies come closer to each other. You see here quite a good energy gap here. This is energy which is going up. This energy gap is quite high for the lithium. But for the beryllium, it is like this energy difference is little bit lower than the lithium molecule. Now if you go from beryllium to boron, it further decreases, you see. And now boron to carbon, it further decreases. And for carbon to nitrogen, they are coming very close to each other. But when we move from nitrogen to oxygen, energy alters actually, right? This comes down right? And this goes up because when you have the smaller size, electronegativity is very, very high, effective nuclear charge is very, very high, and this is the region this energy alters, right? And then you see, and once it is actually altered like that, and then it goes, this difference goes bigger and bigger. For fluorine, it is now bigger, right? So for lithium to nitrogen, you will follow this one. But if you want to draw for the oxygen, so what you will do, you will switch this sigma orbital down and these two you will shift up, while there is no change in the anti-bonding molecular orbitals over there. I hope this is quite clear to you, and it is very important to understand this thing to all of you, right? I hope this is quite clear. And you know, sigma is always your G rate, bonding one is G rate, and anti-bonding one is G rate, right? And in this lecture, in the earlier part of the lecture, I already told you sigma P is G rate while pi are un-G rate. And reverse will be true for the anti-bonding molecular orbitals. Pi anti-bonding would be the G rate one, and your sigma anti-bonding would be the sigma anti-bonding would be the un-G rate one, right? However, it is sometimes very, very important to put the star over there. However, if you write the G rate or un-G rate, then there is no meaning of writing bonding and anti-bonding. But for beginner, it is always good. For beginners, it is always good if you put a star over there, because it is convenient for you only to decide between the bonding and the anti-bonding molecular orbital, right? It is quite important. Now suppose I am going to draw, say your molecular orbital diagram of the lithium molecule, Li2 molecule. So here you will write AOs of lithium. Here again you will write AOs of lithium, and in the center you will write MOs of lithium. Okay, and then you can see here what will happen. See, if you write the electronic configuration for the lithium, right? So I am writing here lithium is having electron 3, so configuration is 1s2, 2s1. This is how I can write, right? But you know, in the bonding, basically your valence electron takes part. So there is no such importance of this core electrons or the 1s electrons, because their effect will be neutralized by the bonding and the anti-bonding molecular orbital. So you can always start your molecular orbital diagram with the 2s only. However, if you want, then you can see just below this, right? Just below this, you can write 1s of lithium and 1s of lithium. Then this will give you the one anti-bonding and bonding. So that their effect would be null, and there would be no effect on the bond order, overall bond order. So you can start from 2s only. Or if you want, then what you can do, you can put that part, right? This particular part just beneath this one, right? So since I have started my diagram with the 2s, so I can count only this one electron, right? 2s electron. Similarly, you are having another lithium atom, right? Li3. So what you will have, 1s2 and 2s1. Since I have drawn my molecular orbital diagram for the 2s atomic orbital, so I'll count only this 2s electron and this 2s electron. Only one electron is there in the 2s, so I can write one electron here and one electron here. If you want, then you can write box instead of this 2s, right? See, because it is not convenient for me to draw the diagram again and again, so I'm using this particular diagram. Rest things are same, okay? And then you see how many electrons I'm having in that case. So 2 electrons are here, 1 electron is here, 1 electron is here, total 2 electrons are there. So according to the Aufbau principle, these 2 electrons will come here. Okay, so this is the, see, forget about the above part. This won't be there actually, because we are not having that much of electrons, so there is no importance of these orbitals. So lithium ends up to here only. So what I can do, right? So lithium ends up to here actually. Now if you want to calculate the bond order, right? If you want to calculate the bond order, so you will write bond order. of lithium, right? Number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbitals divided by 2. So in the bonding molecular orbital you are having 2 electrons. There is nothing in the anti-bonding. Ye khali hai, this one, right? So divided by 2. So again 1. What it indicates? Lithium, 2 lithium atoms are connected with the one single bond only. Please remember, these two are connected with the one single bond only. However, there is not much importance of learning the bond length, right? So I hope this is quite clear to you. But one thing which I forgot to explain in my hydrogen and the helium diagram, I'll go back to those again, right? But here you can see these are the molecular orbital diagram, and in this molecular orbital diagram both electrons are paired. These both electrons are paired, and in the molecular orbital diagram when electrons are paired, that means your molecule is diamagnetic. So your Li2 positive is what? Li2 lithium. Your lithium is diamagnetic. That means if you keep this lithium in the external magnetic field, it would be weakly repelled by the external magnetic field, because both electrons are paired here. There is no such magnetic movement. When there is no magnetic movement, it cannot behave as a magnet. So magnetic field will not identify this lithium molecule. If I go back, similarly on the similar ground, if you see this He2 positive, right? This is the diagram for the He2 positive, right? This is He2 positive. And for this He2 positive, you are finding one unpaired electron here. One unpaired electron you are finding here. When one unpaired electron is there, then it is what? Your paramagnetic, right? So He2 positive is paramagnetic. That means if you keep this He2 positive in the magnetic field, right, then it will be weakly attracted by the magnetic field, right? But for He2, if you have the He2 only, right, without this positive charge, so again one electron would be there, both will be paired, then He2 would be your diamagnetic, right? Similarly, you can identify your hydrogen and others as well, okay? Now, moving to the next one, see, I'm clearing all these things. I don't need this. I don't need this. So I'm removing this. Now I am going for the beryllium ion, right? MO diagram of beryllium. So what I can do, I can shift this the little down, and here I can write MO diagram of beryllium molecule BE2. So beryllium, you know, having the atomic number of 4, electronic configuration is 1s2 and 2s2. Similarly, you will have another beryllium with this atomic number, then it would be 1s2, then another 2s2. Since my diagram, I have started with the 2s atomic orbital, so I'll count only, I'll count only the 2s electrons. I'll forget about this one. This would be cancelled. This would be cancelled out, right? Bonding interaction would be cancelled out with the anti-bonding interaction. So how many total electrons I am having? 4. So, but before starting, what you can do, you can write here atomic orbitals of beryllium atom. Here again you can write atomic orbitals of beryllium atom. In the center you can write molecular orbitals of beryllium molecule BE2, right? While rest of the things will remain the same. This is G rate, right? This is un-G rate, and this is your un-G rate again. This is G rate, right? See, because this I will upload this as a fraction, right? I will divide this entire lecture into the different parts, right? So it would be very, very important for the students to know the basic backgrounds. Okay, don't worry about that. So 2 electrons and 2 electrons, total 4 electrons are there. So what you will do, You will put 2 electrons here, 1 and 2. You will put 2 electrons here, 1 and 2. Now you are having total of 4 electrons. Now it is your duty to fill these 4 electrons in these molecular orbitals, right? In these molecular orbitals. So how you will fill? This will get 2 electrons over there, and this will again get 2 electrons in this one, right? So if you want to calculate the bond order for this one, so what is the meaning of the bond order of beryllium? Number of electrons in the bonding molecular orbital, so these are 2, okay, formula. And then number of electrons in the anti-bonding molecular orbitals, again they are 2 minus 2 divided by 2. This is the formula for the bond order, right? Number of electrons in the bonding molecular orbitals minus number of electrons in the anti-bonding orbitals divided by 2, average, right? So it is 0 by 2, okay? When it is 0 by 2, it is 0. That means BE2 cannot exist. Cannot exist. Please remember, right? It is something very, very important. But if you have, say, now it is quite clear to you. Now suppose you are having BE2 positive. So what will happen for BE2 positive? One of the beryllium atom will have the one less electron, right? One less electron means you can say remove one electron from here. Higher energy orbital will always lose the electron. So this is 2s1. So now if you count here, only 3 electrons are there. 2s1 and 2s2. Only 3 electrons are there. And again I am removing one electron from here. Okay. And similarly I will remove one electron from here because I am having only 3 electrons to fill in these molecular orbitals. So I have filled these 3, 2 and 1, 3. Now if you calculate the bond order for this one, right? If you calculate the bond order for this one, so in the bonding molecular orbital 2, quite fine. In the anti-bonding orbital only one electron is there. So what you will do here, you will remove this, and instead of this you will write 1. That will give you what? Half. Bond order of 1 by 2. 1 bond order of 1 by 2, right? That means BE2 positive can exist and it will have your bond order of half. But if you focus on the molecular orbital diagrams, right? Here you see one electron is unpaired in case of the BE2 positive. One electron is unpaired, okay? So that BE2 positive is paramagnetic. Is paramagnetic, right? But if you have only this BE2 positive, right, it cannot exist. However, sometimes if you can prepare this, right, in any phase, so this would be your diamagnetic, right? This would be your diamagnetic. Why diamagnetic? Because second electron will come here, and molecular orbitals when have the paired electrons, nature is the diamagnetic. So this is how you can explain the molecular orbital diagram of the beryllium as well. So now let us discuss the molecular orbital diagram of the B2 molecule. So this I have explained, Now I am going to explain this particular one. As I already told you, the diagram will remain the same from the lithium to the nitrogen molecule. So this will we will follow this molecular orbital diagram only, right? And this I have explained in my lecture in the pretty much detail why they are G-rayed and the un-G-rayed. So I am not going to discuss this thing again and again. But right from the basics, if we stick on to the basics, so first of all, what we will do, we will write the electronic configuration of the boron. Boron is having the atomic number of 5. So it is 1s2, 2s2 and 2s1, right? Similarly, you will have your second boron atom, right? For beginners, I am writing this thing, I am repeating this thing. However, it is enough to say that it is diatomic, 2 molecules, 2 atoms are there, right? So, but for beginners, I am writing like that only, okay? So, here you will write atomic orbitals of boron atom. Here again on the right hand side, you will write atomic orbitals of boron, okay? but in the center you will write molecular orbitals of B2, and don't forget to write over there not to the scale, because we haven't defined any scale for this energy correlation. So it is always important, right? Now if you check the total of electrons, since I have started my diagram with the 2s atomic orbital, so I'll take account of only the 2s orbital, right? 1s2, 2s2. I am sorry, what I made a mistake. 1s2, 2s2, 2p1, 1s2, 2s2, 2p1. I am sorry for that, right? So now how many electrons I am having? If you see here, 2 and 3, 4, 5 and 6 electrons are there. So first of all, I will fill these 3 electrons in the atomic orbitals, right? So 2s is having 2 electrons, as you can see. This 2s is having 2 electrons, but 2p is having 1 electron. So I will put 1 electron here. Just like that. Similarly, I will put 2 electrons here because it is again the boron, and 1 is here. So if you count the total of the electrons, this is 2 and 1, 3, 4, 5 and 6. So total 6 electrons I am having, and I have to fill these electrons into these molecular orbitals, right? Into these molecular orbitals. Like atomic orbitals, molecular orbitals can also accommodate only 2 electrons. So these 6 electrons will go like that. 1 and 2, 3 and 4, and then you see 1 in this one and 1 is this one, right? These two are the different pion. Remember, these two are like that only, right? 1 electron in this one and 1 electron is in this one, right? I hope this is quite clear to you for boron, right? So now if you see, if you want to calculate the bond order, so how we can calculate the bond order for the boron? Bond order equals to number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding orbitals divided by 2. So how many electrons are there in the bonding molecular orbitals? So this is bonding 1, 2. These two are again bonding, so 3, 4. So these 4 electrons are present in the bonding molecular orbital. Remember, these two s atomic orbitals are combining, they are forming 2 molecular orbitals. One is bonding, another one is anti-bonding. Similarly here 3 are combining, px, py, pz, px, py, pz. So they will form the 6 molecular orbital. Out of this 6, 3 would have the lower energy, bonding, and 3 would have the higher energy, right? So here you see, in the bonding molecular orbital, you are having 4 electrons, 2, 3 and 4 electrons, right? So here you will write 4. Minus in the anti-bonding orbitals, you are having how many? Only 2 electrons, right? So you will write minus 2 here, and this should be divided by 2 equals to 1. That means boron is connected with another boron atom with this B, and it will exist. Say BE2 does not exist, but it will exist, right? This is the bond order, right? But if you want to know the magnetic nature or the magnetic behavior, then you have to focus on this particular molecular orbital diagram. Here you see, this is unpaired electron, this is another unpaired electron, right? These two are unpaired electrons, right? When these two are unpaired, so what will happen in that case, right? So this is paramagnetic in nature, right? This is paramagnetic. So I am writing here, this B2 is paramagnetic, and if you want to calculate the magnetic moment, so that will equal to under root n times n plus 2, where n are the number of unpaired electrons. So under root, how many unpaired electrons are there? 2. So 2 times 2 plus 2, 2 plus 2, 4, 4 2s are 8. Under root 8 is the magnetic moment. Bohr magneton is the unit. Please remember, Bohr magneton is the unit, right? This is Bohr magneton, right? So this is the molecular orbital diagram of B2. I hope this is quite clear to you. Now suppose if you have, instead of B2, you have to draw for B2 positive, right? So if you want to draw the molecular orbital diagram of B2 positive, what you will do, what is the meaning of that? Meaning is that means this B2 is having one electron less now, because one positive is over there. One electron less means you can remove one electron from this P, because see, either from this P, or if you want, then you can remove from here only, right? Only one positive is there, so I'll remove only one electron. And for the correction, I'll write B2 positive here, right? So now how many electrons I am having total? 2, 2, 4 and 5. So I have to fill 5 electrons in these molecular orbitals. So 2, 2, 4, and then again I'll remove one electron from here. This BE2 positive is still paramagnetic, but its magnetic moment would be low now. Why? Because unpaired electron is only 1. So here N was 2. In case of the B2, it was 2. But B2 positive, it is 1. Only 1 electron or 1 unpaired electron is there, right? So for clarification, I can remove 1 electron from here also. So for B2 positive, your magnetic moment equals to, in the bonding molecular orbitals you are having 3, and in the anti-bonding you are having 2. So over 2, that is half. That is no, I have calculated the bond order, this one, I am sorry, not magnetic moment, this is the bond order, right? So half is the bond order for this one, right? Paramagnetic, but bond order is half, and here bond order was 1. That means B2 is more stable than B2 positive, right? And now if you want to calculate the magnetic moment for this one, so how you will calculate the magnetic moment? This equals to under root n times n plus 2. So here number of unpaired electron is 1. So 1 plus 1, that is 2. 2 ones are 2, under root of 2. So for BE2 positive, for B2 positive, right? This under root 2 Bohr magneton is the result of your magnetic moment, right? And for B2, it was something else, right? Like that, it was your under root 8. So this is how you can draw the molecular orbital diagram of the B2 positive as well, right? See, in the earlier case, in the lithium and in case of other things, I didn't calculate the magnetic moment. If you want, then you can calculate the magnetic moment for them also, or I'll try to edit those magnetic moment as well, right? So I hope this is quite clear to you. Now moving to the next one. See, now I'll move to the carbon. So for carbon, I need to remove all these things. So I'm removing these. Molecular orbital diagram will remain the same. So now I am discussing MO diagram of C2. MO diagram of dicarbon, that is C2. Carbon is 6, 1s2, 2s2, 2p2. And since we are drawing for diatomic molecules, so it is good to write another configuration for another carbon atom, 2p2. Since my diagram has started with the 2s atomic orbital, so I'll take account only of these electrons, right? And it is again mandatory, in the left hand side you will write here atomic orbitals of carbon. Here again you will write atomic orbitals of carbon. Here you will write in the center molecular orbitals of carbon molecule, that is C2, right? And then you see the electrons, 2 electrons in the 2s orbital. So you will write the 2 electrons in this 2s orbital like that, okay? And then similarly it will also have 2 Okay, and then 2 electrons in the 2p orbital. So you will write 2 electrons here also, 1 and 2 with parallel spin. Remember, this would be like that, right? 2p orbital, px, py, pz, right? So 1 and 2. Similarly, for this again, 2 electrons, 1 and 2. That means 1 and 2, right? Either this or this. I am writing or. Don't get confused. Okay. So in the atomic orbitals, starting from the 2s orbital, how many electrons you are having? 2, 3 and 4, 5, 6, 7, 8. So I have to accommodate 8 electrons in these molecular orbitals. And like atomic orbitals, you know, molecular orbitals can also accommodate 2 electrons and will always follow the above principle, Pauli's exclusion principle and Hund's rule. So 2 electrons here, 2 here, 4, right? And then 6, 7, this is Hund's rule, right? Sorry, 6, 2, 2, 4, 5, 6, and then 7 and then 8, because it is just like that, splitted, right? So this is your pi 2py and this is pi 2px, right? Z will always form the sigma bond as I have explained to you. So this is the molecular orbital diagram of the carbon. If you want to calculate the bond order for the carbon, that means number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbitals over 2. So how many electrons are there in the bonding molecular orbitals? So this is bonding, 2 lower in energy. These three are also lower in energy, but these 2 are having only electrons. So 2 to 4 to 6. How many electrons are there? 6 electrons are there in the bonding molecular orbital. So you will write 6 here. And in the anti-bonding molecular orbital, you are having the 2 electrons. So 6 minus 2 divided by 2, right? That means 4 by 2. 4 by 2 means you will have 2. That means carbon double bond carbon is there, right? Carbon double bond carbon is there, right? This is the bond order. And now you can check whether it is diamagnetic or paramagnetic. To check the magnetic behavior, you always focus on these molecular orbitals. You see, all electrons are paired in the molecular orbital diagram. See, don't consider your atomic orbitals, because atomic orbitals having 2 unpaired electrons. But we need to consider the molecular orbital to analyze the molecular orbital diagram for these molecular orbitals, and these molecular orbitals having all electron paired. So your carbon is diamagnetic in nature. Carbon is diamagnetic. Diamagnetic, that means weakly repelled by the external magnetic field, right? So if you want, then you can draw this for a C2 positive as well, right? Suppose you are not having this C2, you are having C2 positive. So here I am writing C2 positive. So positive means deficiency of the 1 electron. Deficiency of 1 electron. So what you will do here to show the deficiency of 1 electron? Remove 1 electron from here, right? This I am removing, right? This can confuse you. I am removing this one. Okay. Now how many, see, we have to change this as well, right? C2 positive I will write, because I am drawing for C2 positive now. Okay. So how many electrons? 2, 3, 4, 5, 6, 7. 7 electrons are there. So we will fill the 7 electrons here. 2 to 4, 5, 6 and 7. That means I have to remove 8th electron from here. So I am removing 8th electron from here. Okay. So what has happened here in that case, right? What has happened here in that case? Here you see 1 unpaired electron is there. When 1 unpaired electron is there, then definitely your C2 positive. So I am writing positive here, right? C2 positive is your paramagnetic. C2 positive is paramagnetic. If it is paramagnetic in nature, then you can calculate its magnetic moment. Magnetic moment equals to what? Under root of number of unpaired electrons times number of unpaired electrons plus 2. Unpaired electrons are 1 in there. One unpaired electron is 1 only. So 1 plus 2, that is 3, right? So it is under root of 3, right? This is the magnetic moment. Bohr magneton is the unit. Please remember, Bohr magneton is the unit, right? And if you want to calculate the bond order for this one, so how the bond order will go? Number of electrons in the bonding molecular orbitals, and these bonding molecular orbitals are having 5 electrons now. How 5? 2, 3, 4 and the 5th one, right? And in the anti-bonding it is 2. So you will write minus 2 over 2, that means 3 by 2. So this is the bond order for this one, right? It is 3 by 2, yes. 5 minus 2, okay, sorry, 5 minus 2 is 3, not 5 actually, right? 2, 3, 4, 5, yes, 5 minus 2, it is 3 by 2. So bond order for C2 positive is 3 by 2. So this is how you can explain the molecular orbital diagram of carbon as well, right? I hope this is quite clear to you. See, now let us discuss the molecular orbital diagram of the nitrogen molecule, right? First, I will explain the MO diagram, magnetic properties, bond order, right? Magnetic moment, all these things for the nitrogen molecule. And then I will go for the N2 ions, right? N2 positive, N2 negative, N2 negative, right? So all these things. So now, because this is very, very important in the examination, examiners generally ask about the molecular orbital diagram of your nitrogen molecule. So I am starting this with a fresh idea, right? That means I will not follow I will not actually draw the diagram which I have shown you this for the rest of the molecule, but I will draw the fresh one here, right? So what is the thing we need to do? First of all, you will write you will draw this arrow like that, okay? And that arrow is the thing, but it is the energy which is going up. And you know, your nitrogen is what? Atomic number 7, 1s2, 2s2 and 2p3, right? Since I don't have that much of space, so I will start my diagram with the 2s of the nitrogen, right? I will not draw the molecular orbital of molecular orbitals for the 1s orbital. However, this will because this will not make any difference in the calculation of the bond order or the magnetic properties, right? Because these are the core electrons and they are nothing to do with the bond order and the your magnetic properties, right? So I am not drawing this one. If you want, then you can draw, right? And what is the important thing which we need to remember here? Sorry. First of all, you will divide your page into the 3 columns, right? 3 columns. Here you will write atomic orbitals of nitrogens. Atomic orbitals of nitrogen atom. And at the right also you will write atomic orbitals of nitrogen atom. And in the center you will write molecular orbitals of nitrogen molecule. This is very important. And then here you can write not to the scale. Not to the scale. Okay. And I'll start with the 2s, right? So this is your 2s of nitrogen. So I'm writing here 2s of nitrogen. And above this you are having 2p of your nitrogen. So you can call it as 2px, 2py or 2pz. You can call like that, right? Since it is a diatomic molecule, so just parallel to this, right? Please remember, see, I'm not, I don't have any scale. So to actually give you the exact parallel line, but please remember when you draw in your examination, So these two orbitals must be in the parallel line because they are the identical in energy. So their energy are same and energy is going up. If you actually shift this position either above or below, this will make the energy difference between the two, which is not true actually. So that's why they must be in the same line, right? So this is again your 2s and then this is your 2p. Okay. Then if you want, then you can write this is your 2px, this is your 2py, and this is your 2pz, right? This is how you can understand the things. Now the electrons, you see 2 electrons in the 2s and 3 electrons in the p. So you will fill the electrons here. 1, 2 and 1, 2, 3 in the light of the hood soul, right? Here again, this is 1, this is 2. So this is 1, this is 2, this is 3. Now we will apply the molecular orbital theory. So two of this atomic orbitals will combine to give you the two molecular orbitals. One will have the lower energy than the combining atomic orbitals and other will have the higher energy, right? So you will write here this and this because these two combining orbitals, right? These two combining orbitals are s orbitals, and you know an s orbital where they combine, they form sigma bond only, and it is the bonding one, right? And once bonding is forming, so definitely one anti-bonding will also form. When you put the star on the sigma, it represents the anti-bonding, right? And if you want to put the symmetry of these orbitals as well, so it is very important to remember the sigma bonding is the G rate. Sigma bonding is the G rate, right? And sigma anti-bonding is the un-G rate, right? So since I have cut this particular molecular orbital diagram of nitrogen atom from my entire video. So if you don't know about the G rate and un-G rate, you can go to the complete lecture as well. I will give you the link in the description box for this one. So now you can see these three are there. So they will form the 6 molecular orbital because 6 atomic orbitals are combining. And out of this 6 orbitals form, 3 will have the lower energy and 3 will have the higher energy. So in the bottom, you will have the 2 orbitals which are actually the pi bond. So you can write here pi, and it is formed by the p orbital, right? Px orbital. So you can write here pi 2px. And this one, your pi 2py. Please remember px and py for the linear molecules, right? Form the pi bond, and pz actually form the sigma bond, right? And here again, this is your next, which is sigma, and sigma is formed by the 2pz. So these are the 3 orbitals, and then 3 anti-bonding will also form. So 3 anti-bonding orbitals will look like this: pi anti-bonding, 2px, pi anti-bonding, 2py, and just above this you will have your sigma anti-bonding. I'm sorry, diagram is not very good looking, but factually, or you see technically, it is quite correct. So it is where sigma anti-bonding 2pz. This is how you can form this one, right? Or if you want to know the centrosymmetric nature, right, or G rate or un-G rate nature, so I have already explained you, your pi bondings are basically un-G rate orbital. So you can write U here, where U stands for the un-G rate, right? And your sigma is basically your G rate, so you can write G here. And reverse is true. At the top, pi anti-bonding is basically your G rate, so you can write G over there, and sigma anti-bonding is un-G rate, you can write U here, right? If I go back, then you can see this thing in the more clearer way, right? See pi bonding un-G rate, sigma bonding G rate, pi anti bonding G rate, sigma anti bonding G rate, UG. This thing I am drawing here actually, right? So this is the molecular orbital diagram of the nitrogen atom. Now you have to fill the electrons in it. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Total of 10 electrons are there, and you need to accommodate these 10 electrons in these molecular orbitals. So how I'll fill, please focus here, how I am doing. 2, 3, 4. Now Hund's rule. 5, 6, 7, 8, 9 and 10. Right? So I have accommodated these 10 electrons in this molecular orbital. So now if you want to calculate the bond order of nitrogen molecule, bond order. So what is the bond order? Number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding orbitals divided by 2. So now count the electrons in the bonding molecular orbitals. 2 to 4 to 6 to 8, because this is lower in energy. Out of these two, this is lower in energy, this is bonding. Out of these 6, these 3 are the lower energy, they are the bonding one. And in the bonding orbital, you are having 2 to 4 to 6 to 8 electrons. So we will write 8 here. Minus number of electrons in the anti-bonding electrons. So this is only the anti-bonding electron which is occupied. That means which is having the electron. So 2 electrons are there. So we'll write 2 air divided by 2, this will give you 6 by 2, that is 3, which means nitrogen forms triple bond with the nitrogen. Right? I hope this is quite clear to you. There is no problem in that. Right? Very important. Very, very important. Okay? Now if you want to know the magnetic behavior, I am writing magnetic behavior. Magnetic behavior. So for magnetic behavior, you need to check the molecular orbital diagram. If your molecular orbital diagram having all the paired electron, then your molecule is the diamagnetic in nature, right? Since it is since all the electrons are paired in the MOs. Please remember, don't focus on the electrons present in the atomic orbitals. You focus only on the electrons in the molecular orbitals, and these molecular orbitals are not having any unpaired electron, all are paired. So the magnetic behavior would be diamagnetic. That means nitrogen, if you keep your nitrogen in the magnetic field, it will be weakly repelled by the external magnetic field. This is known as the diamagnetic nature. And for diamagnetic substances or molecules, your magnetic moment value is 0. So this is the MO diagram of your nitrogen, right? Say now suppose if you want to draw the MO diagram for N2 negative, and now I am drawing for the N2 negative. And if you are drawing for the N2 negative, you need to write N2 negative here. N2 negative means one extra electron is there. Negative means excess of electron. 1 negative means excess of 1 electron. 2 negative means excess of 2 electrons. So 1 negative is there, that means 1 extra electron is present, and you can put this extra electron in any one of the atomic orbital. I am putting here. Now I am having 1 extra electron. Total electron, if you count here, 2 or 3, 5 to 7, 7 and 4, 11, and 2 to 4 to 6 to 8 to 10. Now you left with the 1 electron. Where it will go? It will come here. Right? When electron comes here, then the bond order would change now. Earlier, your anti-bonding molecular orbital, see, if you forget about this one, your anti-bonding molecular orbital is having 2 electrons. Now your anti-bonding for N2 negative, 3 electrons are there, right? 1 here and 2 here. So here you will write 3 again. So instead of 2, you will write 3 here. What it means that it is now 5 by 2, and the bond order would be 2.5 in that case. 2.5. right? That means it is less stable than the nitrogen. So it is actually the, you see, kind of fractional bond here, not complete bond, right? So bond order is 2.5 in that case. Magnetic behavior, if you want to check, now it is having one unpaired electron, and whenever your molecular orbital diagram is having any unpaired electron, then the nature of your molecule would be paramagnetic. So this is paramagnetic. N2 negative is the paramagnetic. Please remember, right? Paramagnetic means N2 negative will be weakly attracted by the external magnetic field. And if you want to calculate the magnetic moment for this one, that is mu, magnetic moment equals to under root of n times n plus 2 of Bm, that is Bohr magneton, right? Bohr magneton, where n is the number of unpaired electrons. So how many unpaired electrons are there in that case? Only one unpaired electron is there. So 1 and 1 plus 2, 3. That is under root 3 Bohr magneton is the magnetic moment of this N2 negative. This is how you can draw for this one. Now suppose if you are having 2 positive over there, 2 negative over there, so you will add 1 electron more here. And then the bond order further decreases because your electrons are adding in the anti-bonding molecular orbital. And whenever your electrons are adding in the anti-bonding molecular orbital, it increases the anti-bonding interactions pretty large and decreases the bonding interactions in that manner as well, right? So your ion or the molecule becomes very, very less stable, right? So for N2 2 negative, it is your homework how you will do. And now suppose you have been asked for, say suppose N2 positive, right? Suppose now N2 positive you have to draw. So for N2 positive, first of all, I have to remove all these things. N2 positive, right? I'm drawing for the N2 positive. Okay. So I need to remove this one as well. And 1 electron from here as well. Right? And 1 electron from here as well, and 1 electron, 2 electrons from here as well. Right? So I have removed 2 electrons. Because it is N2 positive, so definitely 1 electron would less. So here you see 2 and 3, 5, because outermost is having 3 or 2, 5. So 5 is here. But second one is having 1 deficient, so 4 would be there. So 2, 3 and 4. Right? Now I have to accommodate 9 electrons into it. So 2 to 4 to 6 to 8 and 9. Right? So again it is, you can see here 1 unpaired electron is there. That means N2 positive as well is paramagnetic in nature, because 1 unpaired electron is there. It is paramagnetic in nature, right? It is paramagnetic in nature. And see, if you calculate the say bond order. So how you will calculate the bond order? Number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding orbitals over 2. So number of bonding electrons you can calculate 2, 2, 4, 2, 6 or 1, 7, right? So you will write 7 here minus number of electrons in the anti-bonding. So only 2 anti-bonding electrons are there. So you'll write minus 2. So this will give you the 2. And again it is 5 by 2. And 5 by 2 means it is again 2.5. Right? And then if you want to calculate the magnetic moment, magnetic moment is what? Under root of n times n plus 2 Bohr magneton. Right? So here under root, and here you see 1, 1 plus 2, that is 3, under root of 3. Right? So this, see, you see, if you have just seen that for N2 negative, your bond order was, your magnetic moment was like that, right? And your your magnetic moment, your bond order along with the magnetic moment, your bond order was also like that, N2 positive. That means your N2 positive and N2 negative, in case, see, when you consider the bond order and the magnetic moment, right, they are same. Okay, but there must be some difference between all these. So first of all, you are having nitrogen N2, bond order of 3. Then you are having your N2 negative, bond order of 2.5, and then you are having N2 positive, bond order of 2.5, right? But which one would be your stable species, right? Definitely this N2 positive would be the stable species. Why stable species? Because you have removed the, sorry, this is your unstable, not stable, this is your unstable species. Okay, because you have removed one electron from this to form N2 positive ion. But if you are forming N2 negative, then you have to put one electron here. Again, this will increase the anti-bonding interaction. So there would be little difficulty in deciding the stability of these two ions, right? So this is how your molecular orbital theory works for N2, N2 negative, N2 positive, N2 negative. For any ion, you can do the calculations on. You can decide the bond order and magnetic behavior as well. Now I am giving you a homework. Among all these three species, which one would be the among these two, between these two, N2 negative and N2 positive, which would be stable, right? Or see whether this one is stable N2 positive or this one, or both are equally stable. This is your homework. In the next class, where I will start the molecular orbital diagram of the oxygen and your fluorine, then I will explain this thing as well. But right now I am giving you the homework, right? So I hope you enjoyed the entire lecture on this particular molecular orbital theory. And please remember, in the initial part where I have drawn the hydrogen molecule He2 positive, Li2 positive, there I didn't calculate the magnetic moment and all these things. And if you want, then you can calculate the magnetic moment and all these things there as well. Okay, so this is how you can draw the molecular orbital diagram for this one, right? I hope this is quite clear to you. So I'll meet you in the next lecture, right? So that's it for today. Thank you very much.